Hello and welcome back. Okay, so in the last video I built this, which was the most basic possible VGA interface to my CPU that I could imagine. All it really is a latch which is taking data from the CPU on command and then a bunch of resistors that allow me to output that data into the VGA cable. But with that I was able to get a basic image out on a VGA display. But today I want to go a step forward. Now this one is very much smoke and mirrors. All the real work is being done on the CPU. And the next logical step, I think, is to get the sync generated in a piece of hardware. Now we started off with the 25.175 MHz crystal. And before I do anything else, I want to see if I can make this work stable in a breadboard, because I know we're right up the top of the frequency range that people recommend using breadboards for. Let's get the oscilloscope out and take a look at this. Okay, so we're getting 25.175 MHz out of there. Now, these extra bits of wire we've got here are probably not helping very much getting a clean signal, but the sync generation doesn't need 25.175. So I'm going to suggest we implement the divide by 16 with a 74LS163 counter. It's power and ground. So this is the parallel load line and a trickle input. The parallel enable is active low, so we're bringing that high to disable it, whereas the trickle input is active high, so we're enabling. Okay, I've got the colour wrong around. There's the other enable input. It's the active low reset line we want to pull high. Now let's feed that clock into the clock line on the chip. Now we're doing a divide by 16, so we want to be looking at that line up the top. So that's the fourth bit, or bit 3, with a 0 base. Excellent, so there's our 1.57 MHz, which is 1/16 of the 25 MHz clock rate. We're seeing a bit of bounce here that we don't like, but once again, I think that may have a lot to do with these lines. Now I do want to see how much of the bad signal we're seeing here is actually the circuit versus me using these awful extra wires. I keep being told to use these little springs. That does look a lot better. Not exactly a square wave, but that is a much cleaner signal. Now, using the probes in this configuration is actually very unwieldy, which is why I've got a little side project I'm going to start up on making some probes designed for doing this. Now something else I want to try is this 163 is being driven at the full 25 MHz, and the decoupling just by sticking a capacitor on the side of the rail here is not very good. So I have got a couple of these which are special sockets with the decoupling cap built in. I would like to see if that makes a difference. Okay, it looks like the bounce at the start has improved. Okay, that's cool. We've got the 1.57 MHz signal we wanted. Okay, now we've got the beta clock for the sync signals. I would like to talk about the different ways we can turn that into the VGA sync. The horizontal and the vertical are very similar to each other, so I'm going to focus predominantly on the horizontal sync. So let's have a think about what those signals need to be. We can think about the scan line in terms of regions with different meaning. We've got the visible region in which we want to output the color data. We've got the horizontal blanking interval made up of the front porch, the sync signal and the back porch. So we obviously need to generate the sync signal to output to the monitor, but also for this entire blanking interval, we want to generate a signal we can use to control our color generation circuitry. Vertical is basically the same but with different timing intervals, And we need to combine the horizontal and vertical blanking intervals to create a combined signal. So thinking about a circuit that can generate these signals, it's very clear there's lots of different approaches we could take. So I'd like to talk about 3 approaches that occurred to me and explain why I picked the one I did. So the obvious first thing that occurred was hardwired logic. Now to think about the circuitry needed, I broke down the bit pattern that would be coming out of counters that were incrementing for horizontal pixel count. So what we're really talking about here is a circuit that can take the binary pattern of these different regions and turn it into the 2 signals we want. We're also going to need a reset on this final configuration to bring the counter back to 0 to repeat for the next line. And so I worked out this circuit. I won't bother breaking this down in detail, but it's mostly a case of looking at the commonality for the different segments and working out the gate combination. It's possible this could be simplified a little bit more. I worked out roughly how complex it was going to be and figured this was in the ballpark of a good implementation. The vertical version would be larger because we've got more bits on the line count, and so we can expect the logic circuit to be a bit more involved. The limitation with doing this with hardwired logic is we've got very little opportunity to tweak the signal easily if we decide there's something not quite right or we want to look at different VGA modes. So the next thing I looked at was a more configurable logic arrangement. So this would be a slightly larger circuit. It's based on this very simple principle of we take a set reset latch and then we have counters where the carry out are triggering the set and the reset to generate the output signals. So we have some mechanic to initialize the counter when it gets reset. And so by setting these registers, whether they be CPU settable registers or perhaps something on dip switches, we pre-initialize these counters and control the time interval before the carry signal. And so adjusting these, we could make whatever output signal we want at the cost of a higher component count. But I quite like this, and most video cards have something that's configurable like this in them, although I don't know whether or not they'd use exactly this kind of arrangement. And so I'll move on to the third idea I considered, which is to use the same approach we've used in the pipeline, which is use ROM chips to implement some combinatory logic. So if we use 4 of these 163 counter chips, 4 bits apiece, as an index into a ROM chip, then the data contained in there can encode all of the main signals we want, including the reset signal and the combined blanking interval. And if we find we need to tweak the signal at all or look at different resolutions, we just need to modify the contents of the ROM chip. So I really like this. And it's actually a very simple circuit. We should be able to fit this on about 1.5 breadboards, and that's going to leave us a bit more space on the desk for some of the more interesting stuff we're going to be getting to later. So this is what I'd like to implement. Now these ROM chips are comparatively slow though. The ones I have are in the order of 150 nanosecond to update their data output, and so I'm going to put a latch chip on there to latch the outputs. So we've got a very controllable latency on the lookup. Let's go and look at building this. So we only need 15 bits of address, but this will give us 16 bits because the counter's coming units of 4 bits. That's power and ground. Now on this first one, we need the count enable to be on for both of them. We need parallel input disabled. We want that on all of them. So we've got the terminal count, what we'd normally call carry, is here on pin 15. We'll drive the count enable lines of the other 3 chips with the predecessors. Other count enable lines need to be high. Now pin 1 is reset, and we're going to want to be able to control that. So I'm going to wire all of those together. Now on the 163s, counting is controlled by the count enable lines, and the chip should always receive the clock. So I'm going to wire all of those together as well. Right, so reset is active low, so let's pull it high for now. And we take our 1/16 clock and feed that in there. Okay, in theory, this should be able to count up to 65,535 now, and then trigger the carry out the top. So that means we should see the carry line here ticking 24 times a second. Let's check that, and that will confirm that this circuit is doing roughly what we expect. Hertz, that's exactly what we wanted to see. We're going to need some more breadboard space. Now we've got 16 address lines here, 15 of which we need to bring out to a ROM chip. Now we're going to need some test data. I'm going to have to write some program code to actually generate the ROM contents with all of the bits in it. But what we're just interested in right now is that reset bit. And we know from the last video we've got 800 pixels across, divided by 16 for our clock divider, and we've got 525 lines. So that means address 26,250 needs to contain the reset bit. So in hex that's 668A. So now I've got 1 byte of data in this ROM set to something other than FF. Let's burn that, and it should give us a nice first test. So it's ground and VCC. Write enable, we pull that high. So there's chip enable there, we want that low. And output enable low as well. So now we've got the data output lines, 3 of them there and 5 of them there. And then all the other lines are the 15 address inputs, which we need to take from here. That's annoying. They're a different way around here than they are over here. Now the first 8 address lines are all in a row, which makes it easy. Right, so in theory, we should have the reset signal necessary to change this from 24 Hertz to fractionally under 60 Hertz on any of these data pins. $59.9 Hertz, that's just what we wanted. Awesome. We do want a latch chip in here to grab the outputs. This is the 74LS574 hardwire output enable. And the main reason we want this is for the copy line to come from our clock. Right, that's the 8 data lines coming out to the latch chip. I've put 0 on the left. I'm going to put these around the other way or I'll get confused later. Now we should be able to take a look at the reset signal coming out of the latch chip. So as we would expect, it gets pulled in 1 cycle behind. Now we need to work out the way of getting the correct data onto this ROM. So we need to write some code to generate that. Alright, now writing this code from scratch is going to be annoying. Right, I'm going to make a new project for this. This should be quite a simple piece of code. Right, so firstly I just need to write a chunk of code to generate the binary data blob, and then we'll pay a bit more attention to filling it in. Okay, so we've got 50 clocks on the horizontal and the first 40 are the visible area. Okay, so I think I've set the flags right for the sync and the blank. Reset is an active low, so I need to do that. Okay, that's cool. It looks like the right pattern. Right, when I created the ROM before, I put the reset flag 1 byte later than it should have been. Would have been almost impossible to tell the difference, but worth remembering. So this should have the correct sync data in it. Let's see what we get. Right, so we moved reset to the 3rd bit. There you go, 59.94 Hertz. Now the topmost bit was horizontal sync. That's 31.46, that looks correct. Horizontal blanking looks correct as well. Vertical sync. And vertical blanking. That looks an awful lot like a VGA signal. We should have a combined blanking signal there. That's awesome. Right, we don't have any image data, but I think we can actually make the monitor at least recognize we've got a signal. Right, so that was our H-sync, and that was our vertical sync. Let's plug these together and see what we get. Okay, it doesn't like that. Don't know what these color signals are doing. So the top of it is horizontal sync. Okay, I've got a sneaking suspicion this might be working, but because we're not actually outputting any color, it's not telling us. So I thought maybe it would indicate the resolution on the screen, which most of my monitors do. Right, so this is a small monitor I've got, which hopefully will indicate the resolution and tell us we've got a good signal. Right, so yeah, that's detecting 640 by 480. That's good. Now we need some color data. Okay, so these sync lines we can use as they are, but we need to do a bit of work on the RGB. So this is the blanking signal. And if we feed that to the output enable on this latch chip, that's going to be pretty handy. So now we've got red, green and blue bits, but I think I want to do the digital to analog conversion a bit better than what we've got. Now the red, green and blue signals need to vary between ground and 0.7 volts. So I did work out the resistors necessary to create an R2R resistor ladder that would give us that functionality. Now ideally we'd have 470 and double 470, but 910 is the closest I've got, but I think that's going to be okay. So I'm going to construct a 3-bit resistor ladder for each of red, green and blue. I'll get lynched if I don't put these all in the same way around. Now the big benefit for the R2R ladders to us here is that they do terminate with ground. So when the blanking signal comes on and the output enable of here is disabled, these should all naturally drop down to ground. I think I'm going to do these ones vertically. Okay, so we should have 3 bits for each of red, green and blue here. What we can do with them. Let's connect the monitor back up. So in theory we should have some binary bits in here that we can create some output from. Now the easiest thing we can get at is the counters. That will at least produce a varying output. That's working, but it's very dark. Now high signal should be 0.7 volts. At a guess, we're not going anywhere near that. It's close actually. Obviously we shouldn't achieve the full 0.7 without all the bits set. But I've just realised that we're not actually respecting the blanking interval. We need to hook that up. And we've got 8 bits out of the latch here. So I'm going to do 3 bits for red, 3 bits for green, and 2 bits for blue. Right, for now I'm going to bring the blue to ground, the green to ground. We're going to take the red bits into the counters that come off this chip. Okay, that pattern is in fact the kind of pattern I would expect. Okay, I don't like the flickering we're seeing on this, but I think that might just be some loose wires. I think we're getting the right kind of output. It was the blue line that was loose. That's awesome actually. See, now what we need to do is work out a better way of driving these 8 colour lines. And eventually we're going to need to connect those back up to the CPU, which is what I want to finish off this video with doing. But I'm wondering if there's anything else we can do before then. Now we've got 2 spare lines on the ROM chip. I wonder if we can use those directly. Okay, so what I've done is I've grabbed a image file of the Parrot that I demoed last time, appropriately scaled it and converted it, and I'm outputting a grayscale version of it in the bottom 2 bits. Let's see what we get if we do that. Okay, let's give this a go. Well, I recognise the Parrot there. Right, so 2 of these red lines are the wrong way around. That explains that. We're actually losing the left-hand pixel because we're double latching the data coming out of that chip. Apart from that, that's really good. That's actually a nice simple little circuit that's generating a VGA signal from scratch. We could fit all of that into this bit of breadboard and do the whole thing in 2. That's awesome. Of course, now what we've got to do is interface this back to the CPU and work out a way of driving the colour data directly. So the output data from this latch chip, we need to be able to optionally assert that back to the main bus. And then we want to be able to read the colour data in from the main bus when we write out to the appropriate I/O port. Okay, so just like before, we can take the power and ground from the interface lines. So we're actually going to read from the main bus to get this colour data. I'm going to use a 541 to deliver this data back to the bus. So a colour load line actually needs to come from the port load line. I'm using this 541 to push stuff back onto the bus. This will give the CPU access to those sync signals and the blanking interval signals. One of the output enables is the assert line, and one of them I'm just going to pull low. I have to cross connect the outputs of the latch to the inputs to the 541. And then we need to connect the outputs to the main bus. Okay, so that should be everything necessary to connect this back to the CPU. So I'm going to tidy up all of this stuff, get the CPU back out, and we'll take a look at some code. Okay, let's get this wired back in. It's a main bus connection. Put that into the monitor cable. Now, we're currently deriving the 1/16th clock rate from here, but at the moment we want to sync things up with the processor, and we've got the 3.14, the 1/8 clock rate being generated in here. So what I want to do is drive this off the clock coming from the CPU for now. I think that was there. So we've still got to halve it. So move that along to bit 0. That should be right. Going to get an extra ground line in. Okay, so I'm going to spend some time coding up a way of testing this. Now, I'm not going to bore you completely with that, but I'll show you what I've done when I've finished it. Okay, so I've updated my image drawing code here. Now, before I had lots of very carefully controlled functions to maintain precise timing for the sync generation and interlacing that with the color output, but I've managed to strip an awful lot of that back. So my main loop no longer has the instructions for outputting the horizontal sync, and the individual line functions don't have any extra code in them for managing those sync signals. I've still cycle counted this main output loop, so it is possible now for me to output the full 27 pixels that the clock divider allows me to have with the free cycle unrolled loop. Then the big difference down here is my reset function has code added to it which reads in the vertical syncing data, and it waits for the vertical sync to start, and then it waits for it to end, and then it can proceed comfortably knowing where we're at for the rest of the frame. Okay, so the goal here is to get the Parrot image out, but at a higher quality. Oh, that's awesome. Okay, the big difference here is we've got 256 unique colors, but we've also managed to fill the screen completely, whereas before we had some border pixels when we were still finishing off sorting out the sync timing. Okay, I'm going to put the original Parrot from the last video up. There you go, you should be able to see the difference. That is a massive improvement. Right, so what we've successfully done here is we've completely offloaded the sync generation onto our circuit board. I think we can tidy this up a little bit more, but I may do that between videos. But this would probably have fitted onto 2 breadboards, so that's pretty cool. And we've definitely hit the goal of increasing the quality of the image with every new circuit we've added so far. But actually, more importantly, we've got some free time on the CPU now. So during the main blanking interval, I'm going to try and put together a bit of code that will update the buffer contents and see if we can get something animating, because I think that might be a little bit of a cherry on top for this stage in the project. Okay, this is what I've come up with. I've kind of reduced the vertical resolution a bit, but I've got a slightly modified form of the code here, which can copy the same line out by stepping back the 27 bytes from the image data. So that effectively reduces my vertical resolution to make it a little bit more manageable at the moment, because that vertical blanking time isn't very big. But then I've added this little bit of code that increments the horizontal offset of the data I'm reading and then fills the extra row of pixels in with some new values. And so what we should see here is some rapidly scrolling colors, which will nicely prove we've managed to do some updates. So remember, this Parrot is still on the screen because the code is continuing to execute. So now we see solid red on the screen because the VGA device has stopped being updated by the CPU, but its sync generation is still working. And this kind of reddish color is obviously what was last latched into the color chip. Ah, look at that. Okay, it's not 100% what I imagined when I wrote that code, but that's going to be a a pretty effective demonstration that we were able to update that data in the spare time. That's really cool. Okay, well, I'm really happy with the progress today. Now, the next obvious step to do in this VGA circuit is to give it some RAM, work out a way of interfacing that memory to the rest of the CPU, so then the VGA subsystem can run completely independently, apart from when the CPU wants to update it. So that's going to be pretty interesting, and I know there's some viewers who are going to be very interested to see how I do that. Okay, so I am really pleased with the progress we've made today. We've successfully taken the sync completely away from the CPU, which has freed up some time on the CPU. We've got a slightly more complete VGA subsystem now, although the next video I'll be aiming to integrate some memory and interface that back into the CPU's address space. And that's where things start to get interesting, because we can completely uncouple them then. Well, I hope you found this interesting, and I hope this VGA series is living up to all the expectations I know people have. I'll see you again soon. Goodbye.